In science, we often look at data quantitatively, meaning we make measurements. And when we make measurements, we need to recognize that any measurement has both a number and units. This number has 6 digits. There are 6 digits in this number. But are they all really meaningful? Probably not. This little girl, looking at her height in a growth chart, is more than 3 feet tall. But do we really know to the tenths, hundredths, thousandths, 10,000ths, 100,000ths, do we really know all those digits are accurate? No. So let's start by considering the correct number of digits in a number. And to do that, we need to look at place value. So you know that the digit to the left of the decimal is the ones place. And the digit to the right of the decimal is the tenths place. When we make measurements, how far to the right we go? Tenths, hundredths, thousandths? That depends on the tool. The tool determines how precise our measurement can be. Here we have one object, a blue cylinder, and we're going to measure it with 2 different tools. Here we have ruler A, and ruler A has major divisions in the ones place. I can see that the length of this object is between 4 and 5. So it's 4 and a little bit more, whatever the units are. So in my mind, I'm going to break this into 10 spaces and estimate it. And I'm estimating the tenths place. I'm estimating the tenths place to be 8/10 of the way between 4 and 5. So I would report this measurement as 4.8 units. Now, if it were a real ruler, the units would probably be inches or centimeters, but I don't know what they are. So I'm just going to say this measures in units. And if I was told centimeters, then I could write centimeters. Using a different ruler, but measuring the same object, we see that the major division is the ones place. I am measuring that this is between 4 and 5, so it's more than 4, but less than 5. The space between 4 and 5 has been divided into 10 units, and I can see that this is between the 8th and 9th tenth. So the minor divisions are tenths. And it's 4.8 and a little bit more. If I estimate this to be, by breaking that small space, I'm breaking this small space into 10 units. If I estimate that to be halfway between 4.8 and 4.9, I am estimating the hundredths place. To be 5/10 of the way there. And then I need units. So I've measured the length of this physical quantity with both numbers and units. The first measurement has 2 sig figs, 2 significant figures. A significant figure is every figure that was measured plus 1 estimated. For the object measured with a different ruler, I have 2 measured places and 1 estimated. So it has 3 sig figs. The more lines on a tool measuring this linear scale means more precision. So here, I measured this object using ruler A and said that it was 4.8 units. The number of sig figs is the number of digits I've written. I've written a 4 and an 8, that's 2 digits, 2 sig figs. I'm going to use this idea. How many sig figs? 2 sig figs when I am multiplying or dividing. The other way I might look at this same measured value is how many places past the decimal. And there is 1 place past the decimal. We estimated in the tenths place. I'm going to use that idea when adding or subtracting. Using ruler B, we ended up with 3 sig figs. And there are 2 places past the decimal, the hundredths place is where we did our estimating. Both these ideas are important. It just depends which one do we consider with, are we multiplying and dividing or adding and subtracting when we do calculations with that number. Okay, so degree of precision. Here I have an object, and I'm going to make the assumption that these 3 objects are the same length. We're just measuring them with 3 different tools. And the first tool does not have a lot of lines. The first tool measures between 0 and 100, and I see that it's less than in the hundreds place. So I see that it's less than 100. I'm going to start with a 0. And then I'm going to break this into 10 pieces. And I'm going to say the length of this object is more than 2, but less than 3. What is the next place? So I'm measuring in the hundreds. And the next division would be in the tens place. So that's 20. 10, 20, 30, between 20 and 30. But I added these lines, so these lines don't count for the measurement. I'm going to say this is 20 centimeters. I probably wouldn't put the 0 at the beginning. That's the measured digit. This is the estimated digit. So I only have 1 significant figure to report, and that is this 2. Now, the 0 is necessary. The 0 here is a placeholder. A placeholder is necessary, but it is not significant, because to be significant, a digit must be measured or the estimated digit. Okay, so I have a number here using this tool, and it has 1 sig fig. Measuring that same object with a different tool, I have more divisions. The major divisions are the tens place. So I see it's between 20 and 30. I have measured that too. And now I break this distance between 20 and 30 into 10 equal spaces. And I'm going to estimate that we are 2/10 of the way between 20 to 30. So in the ones place, I'm going to put a 2. Add units. This number has 2 sig figs. Measuring that same object with a better tool, I now have the major division. The major division is the ones place, and I'm measuring it, it's the tens place. I'm measuring it between 10 and 20. So tens place. And then the minor divisions, it's more than 1, 2, but less than 3. So 22 point something. And I'm going to estimate that this is halfway between 22 and 23. And so it's 5/10 of the way from 22 to 23. This measurement has 3 sig figs. More lines means greater precision. When measuring volumes, we're also actually using a linear scale. Here I'm using a graduated cylinder. And a graduated cylinder measures volumes in milliliters. When I look at this graduated cylinder, I'm going to get my eye, there's my eye, right on eye level. So this is me looking at it. And I'm looking at the center where the meniscus is. Oops. The meniscus is the place where the two phases meet. So in the cylinder, we have liquid. And above the cylinder, we have air, gas. And the place where they meet is the meniscus. When I look at the meniscus, I'm looking at down the center. So in this case, I'm looking at the lowest place. I can see that my measurement is, let's see, major division is ones, more than 2 and less than 3. And then this space between 2 and 3 has been broken into 10 spaces. So this is 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, and a little bit more. So I'm going to break this space. I'm going to break this space into 10 equal pieces and estimate how far am I between 2.6 and 2.7. I'm going to say that I'm halfway there. And then add units. There's my measurement. 2.65 milliliters is my volume, reported to 3 sig figs, which is the right way to report it, using this tool. Now, if I had been standing above the meniscus, so instead of having my eye at the height of the meniscus, I was looking down, I would have measured a number that was too low. If I was standing below, looking up, and so I'm still looking at this place where in the center, where the water meets the air, I would have come up with a value that was too high. So it's important when we finally get to the lab someday that when we make our observations that we are on eye level with the meniscus so that we get an accurate measurement. We measure physical quantities, and one of those quantities is mass. Mass is measured in grams using a tool called a balance. When we measure mass, the balance does the estimating for us. Here we have a balance measuring a bowl of blueberries, and the blueberries have a mass of 222.5 grams. The balance has measured, and estimated the last digit for us. Because the place value that is estimated was 1/10 of a gram, also known as the decigram. This tool is referred to as a decigram balance. All balances measure in grams. This tool goes to the 1/10 of a gram, and that's the estimated digit. Things to find the volume. Here we do. We could use a formula for volume for this regular solid, but it's easier just to stick it in water and see how much water it pushes out of the way. And so we call that volume by displacement, and that's what we're doing here. So we start with an initial volume of just water. I'm looking at the meniscus, and I'm looking in the center of the tool, and I'm going to estimate that to be 19.0 milliliters. And that 19.0 milliliters is milliliters of water. And then I'm going to estimate, once we've added the object, what the volume of water and the object in it, what that is. I'm going to call that 29.0 milliliters. To find the volume of just the object, we subtract. So this object had a volume of 10 milliliters. We're reporting this last digit because when we add and subtract, we consider how far past the decimal. This tool measures to the tenths place. And so when we subtract, we have information about what's in the tenths place. The volume of that object is reported to 3 sig figs. Why do we go to the tenths place with this 0? Because the measured values both went to the tenths place. When would we do something like that? Volume by displacement? Maybe when we want to figure out what the density of an object is. So to find the density of an object that is irregular, like this ring, we don't have a formula for that. And so our way of figuring out the volume is to measure the water before and the water after, and the difference of height of water is the volume that that object is occupying. So let's do that. The volume before, 63.1234, 64. Is between 64 and 65, or is it on the line? I would say it's on the line. So I'm going to say it's 64.0. And this 0.0, oops, and this 0.0 is because it's not between 64 and 65. It's on the line with 64. So when we see the estimated place to be a 0, that tells us on the line. And then we add the ring, we make a measurement. $60, $70, 10 places in between. So 61, 2, 3, 4, 5, 6, 7, 8. That's also on the line. So the volume of just water subtracted from the volume of water plus ring, the water cancels out and we get 4.0 milliliters is the volume of the ring. We are still going to the tenths place in our answer because both measurements went to the tenths place. However, the tens place canceled out. 60 minus 60 is 0. So it is possible to lose digits on the left when subtracting. We now have an answer that has 2 sig figs. We would need to use a balance to find the mass. So let's say that we put that on a balance. We found a mass. And the mass of that ring, I'm going to put it on a centigram balance. So we're going to go to the centi of a gram, or the hundredth of a gram. And let's say it was 26.24 grams was the mass. And the volume of that ring was 4.0 milliliters. I'm going to do a little math. And I got 6.56 grams per milliliter. Now, when we're multiplying and dividing, we have to consider sig figs this way. The mass has 4 sig figs. The volume has 2 sig figs. When multiplying and dividing, the answer should have the fewer number of sig figs. So 4 sig figs divided by 2 sig figs. Our answer has 2 sig figs. I'm going to round to the tenths place. And my answer is 6.6 grams per milliliter. That is the density of the ring. Okay, so that's your crash course in sig figs and using sig figs in calculations after measuring. I hope that that's helpful, but I imagine that when you work through the homework problems, you'll probably have questions, which is why we'll be meeting through Zoom so that I can answer your questions. Thank you very much for your time.